Thank you all for joining us for the inaugural Texas FIRST Robotics Competition workshop, hosted by FIRST RGV. A little bit about us, and then we will turn it over to our presenters today. FIRST RGV is a nonprofit founded in 2015 that supports the FIRST community in the Rio Grande Valley, which is an area approximately 3 hours long by 2 hours wide, sits next to the border of Mexico. Yes, in Texas, it's easier to measure by driving hours than miles, just because Texas is just large. Since 2015, we have seen explosive growth of teams in our FIRST LEGO League and FIRST Tech Challenge program, but our growth in the FIRST Robotics Competition program is positive, but we are not where we need to be on ensuring access to the more than 250,000 students in the K through 12 space here in the Valley. With our events like this, we are doing our part to create awareness of our efforts and the need for strong sponsors and mentors to help our community. We are proud Texans, and I'm honored to be part of the FIRST in Texas Robotics Territory. Our organization is proud to be hosting this weekend's event. If we have any technical issues, please remain patient. We will get them resolved as quickly as possible. While you're engaging in the chat, asking questions, and saying hi to your neighboring team, or maybe a team across Texas, we ask that you remain on topic and know that this session is being recorded for teams to take advantage of this great information later. We will post this information on the FIRST RGV YouTube channel, and you can access it directly by visiting youtube.firstrgv.org or by searching for FIRST RGV on YouTube. I want to personally thank the FIRST Robotics Competition teams across Texas that have come together this weekend to make this live event possible, and for the hard work of our FIRST senior mentors and AmeriCorps Vistas across Texas that stand ready to help support our teams. On behalf of FIRST RGV, we hope everyone has remained safe during this pandemic, and we are confident that all of the partners across Texas will be getting ready to bring you a robotics season soon. Thank you.
All right, so welcome to the FRC Pneumatics presentation. This is presented by FRC 2468. So, advantages to pneumatics. So pistons are generally lighter than motors, and although you do need the whole setup, the more subsystems or more pistons you have, the lighter your robot becomes relative to like using motors. Pistons are simple for mounting, and they are very reliable because you only have two positions. You got the extended one and your retracted one. The current draw is normalized, so the amount of current you draw won't change, rather than in a motor, the more stress, the more you have to use it, the more torque it draws, basically, the more load is on it. And generally pneumatic cylinders save space in critical areas in your subsystem. The rest of the setup will go somewhere else on the robot where you don't have that space restriction. Disadvantages to pneumatics. If you only use a few pistons, the weight of the system will be increased compared to motors. So basically, like I said before, the more subsystems that you use pistons in, the lighter your robot becomes. One puncture or leak and your entire pneumatic system is done for. So because the pressure is being leaked, and during competition, you'll lose your pressure and pneumatics just won't work. Piston rods will bend. So the rods that extend out of your pneumatic cylinders, they will bend. And as hard as you try, you will not get them straight again. So you will need to include something to take the stress off of the rods in your design. Pneumatic leaks. So these will always happen at some point during season when you're doing pneumatics. And good ways to prevent these are to always cut straight with the pneumatic tube cutter. You need to use your Teflon tape properly and correctly, and test for leaks as you assemble the system. Finding leaks. So a couple ways to find leaks. If you're in a quiet environment, you may be able to listen for the source, using your fingers to feel for a leak. If the generally leaks, you might not be able to feel them because they're so slight. Using soapy water is a really good way to find possible leak points and you need to watch for the bubbles because air will make the soap water bubble. And if you're still having trouble, you can section off parts of the system, plug open ends up, section off, and let's search for leaks there. Mechanical components, the pneumatic cylinder. This is what is moving your subsystem. The bore size, which is the hollow kind of inside of the cylinder. The larger the plunge area, the more force you have to use in your subsystem. And that plunge area is basically the bottom of the rod that's getting pushed by air. And the larger volume of the inside, the slower the actuation. So you extend slower. The stroke is the length the piston extends. So your rod comes out how much, retracts how much, that all gets included in your design. And generally for mounting, you use clevises and they're very simple. One screw should be enough. The regulator. So this limits the working pressure to up to 60 PSI on the part that the side your pistons are using in the pneumatic system. And storage tanks are often kept at 120 PSI. So storage tanks where you store your pressure on your robot. And the regulators they're always one directional. They regulate the working pressure in one direction, not the other. So the air won't be regulated if it's flowing in the other direction. And the arrow on the bottom of the regulator tells you which way your flow is being regulated. The pressure gauge, this displays the pressure obviously, and it's useful for calibrating the regulator for working pressure and also checking the high side for pressure. So the high side is where the 120 PSI pressures. So your air tank's storing most of the pressure for your robot to use. And this is useful when checking for leaks because if you see that your pressure is going down, there's a leak somewhere and that's not good, especially for the high side where you're not going to have enough compressed air to use during the competition. The flow restrictor, this decreases the volume flow rate into the pneumatic cylinders. These are adjustable, so it decreases the actuation speed of your pistons or your cylinders. It slows the air in one direction and the air can still flow freely in the other. So it's similar to a regulator, but used for just slowing down your actuations in general. And this is good for fixing imbalance systems where maybe you have like two pistons and you have more weight on one of them than the other, but you want them to extend at the same rate. So you can use flow restrictors. You can slow down the lighter side and make it the same speed. Air tanks, this is where you store your air pressure, or the pressure and energy. And these can be used on the low side or the high side of your pneumatic system. And the low side is the side where you're regulating at 60 PSI and that pressure is just use it for extending the pneumatic cylinders. And the high side is where you're storing more of your compressed air. And yeah. You can use the A and B design calculator to determine how many tanks you need on each side or at each pressure. And it is illegal to modify these, so you do not want to paint them, stickers, just don't mess with them, basically. The A and B design calculator, so this is the pneumatic portion of it. And this calculates the amount of air tanks you need. So on the left side chart, you'll put in all your known values for, say, your pneumatic cylinder and the time and cycles, and it'll give you max force and the total volume usage. You'll try to match that up with the chart on the right, where your tank volume, the number of tanks you have and the tank pressure, and it'll give you total tanks volume. So this you have to experiment around with, figure out what's a good match, how many tanks and what size tanks and everything like that. Push to connect fittings, that's what PTC stands for. And this connects everything in your pneumatic system together, the tubing and where the air flows through. And each fitting generally has like 2 to 7 ports on it. So the one in the picture has 3 ports. You want to ensure the tube is cut perpendicular neatly in order to minimize the risk of having leaks. And these are pushed to connect. You push the tube in and it stays in. If you want to release the tube, you press down on the tab. So you can see these kind of separate tabs on the end of in this image, these 3 tabs on the ends, and you press down and you pull out the tube. Threaded fittings. These connect components attached to the compressor, and you must use Teflon tape for all threads. Although you don't want to cover the first threads because you want to actually be able to thread your fitting into the components. And you also use Teflon tape on the threads that will be going into the pneumatic cylinders, which you will be screwing into. The relief valve. This releases pressure if your pressure in your system goes above 128 psi. You cannot go above 120 psi. That's illegal. And this must be directly connected to the compressor with rigid fittings. And that's because if you were to use some type of pipe and it pinched, that would basically mean this relief valve would render useless. And this is very useful in case your pressure sensor malfunctions and you don't know the pressure. And in case it goes over, and that way nothing blows up, it'll just release the pressure. The pressure vent plug. This is where you release all the stored pressure. It must be on the high pressure side because that's where the 120 psi pressure is stored. You use it to vent all the pressure after a match. And when you're doing this, do it slowly. Try not to deafen your teammates because it's very loud in the pit when you're doing it. And these are solenoids. So this is part of the electronics. And you got double solenoid and you have single solenoids. So generally double solenoids are used for double action pistons where the double solenoid has two sections where air flows out into the piston. And your double action piston has 2 spots for air to flow in. And on one end, it'll push the piston rod out, and on the other end, it'll push it back in. So that's the double action. And the single solenoid works with a single action piston, and it pushes the rod out, and it uses a spring to get it back retracted.
So electrical. So there are 4 main components for electrical: the compressor, the solenoids, the pressure switch, and the PCM itself. So the PCM, it basically controls all the pistons and all the pneumatic components that electrical they route into this. And so it can control 12 or 24 volt solenoids, but it cannot do both. And so you can control up to 8 solenoids with it. So the PCM gets power from the PDP and it distributes it to the compressor, the pressure switch, and the solenoids. And so the pressure switch is used to control the compressor, and it's a closed loop circuit. So you can't actually turn on the compressor if you wanted to with code. You can either disable it or enable the entire system of turning it off and on. So the solenoids, as I mentioned before, they can either be 12 or 24 volt. And so there's a little jumper here. You see the label VSOL under it. So that controls all the 8 ports. And so if you wanted to run 12 volts and 24 volts in one robot, you'd have to have 2 PCMs, each with the jumper in different position. So from an electronics standpoint, a single solenoid is wired with 2 wires, and it only controls one end. So it moves one end of the value block. And so when you power it, it would let the air through, and when you unpower it, basically it springs back and shuts the air off. A double solenoid is the same, except it moves the block from both ends, and so that allows, when it's on, air flows one way, and when it's off, air flows through a different port the same way. John?
Sorry, I was trying to share the link. So component layout on the high side. So this is where you're storing at 120 psi pressure. This side must have the relief valve directly attached to the compressor, and it also must have the pressure switch, a gauge, and a vent plug. And the regulator will lead to the low side where it's changing from the 120 psi pressure to the 60 psi.
So a question from chat. What would you do if you find a pneumatics leak? So when you find a pneumatics leak, generally you find it by you've pressurized and maybe 5 minutes later you see you've dropped 5 psi from the high side. That's a pretty big issue because when you're queuing for your match, you don't want to start with less than the max pressure you can have because then you're not starting with as much energy in the system. And so if you find a pneumatics leak, you generally try to pinpoint it using the methods we showed. So you pinpoint it, there'll usually be a connection of some sort. And what you do, it's usually what we found in the past is either the Teflon tape wasn't put on well or has come off for some reason, or the tube wasn't cut straight. So essentially you depressurize the system, cut the tube straight or rewrap the Teflon tape, and then you pressurize again, test if you still have the leak. I hope that answers your question.
All right, so from the regulator from the high side to the low side has all your pistons or the pneumatic cylinders and also the solenoids. And it'll also have the flow restrictor sometimes if you're using those. Also have a gauge and air tanks. So air tanks, they can go on either the high side or the low side or both. Depends on how you want to do the pneumatic system.
So we've told you a bunch of stuff about pneumatics. You might be wondering, how do you design for pneumatics? So when you're designing for pneumatics, you have to think about how far the piston extends and retracts. This is the throw. And so when you do that, you have to eliminate lateral load in the cylinder. This is mainly to avoid bending the actual shaft of the cylinder. And then you got to calculate the force you need and the force you have with the cylinder. So that determines the bore. And so on the right, you'll see an example. This is an actual pneumatic catapult that we designed during one of the off seasons. And so first thing you do essentially is sketch your axis. You'll usually have an axis if you're using pneumatics, but I guess you could be doing a linear thing. And so second, you want to sketch the part of the assembly you intend to move. And so that would be me sketching the top part. And so you actually see, I sketched the pneumatics, that's what they called it, in two different states, in its retracted state and in its extended state. And so what I did is I dimensioned each thing the same. And when you're doing that, you need to avoid horizontal and vertical relations because that will destroy the model when you try to move it. So I created the extended and retracted, and then you have to adjust it as needed, right? So you might have been way off with your throw calculations. And so you need to go back to, say, Bimba, where you're getting your components. And you'll need to change what you're using or change something in your system. So it's a lot of trial and error involved in that. So here's some of our resources. We have the A&B design calculator, which is what we mentioned before. It does pneumatics as well as a bunch of other stuff. Automation Direct is where we get extra components like the regulator. And then, so Bimba air cylinders. Vex has things like ball shifters and more general components. And if you have gotten a kit apart recently, then you actually, the pneumatic parts you get in there are from AndyMark. Does anyone have any questions? Yes.
All right. 2468, thank you for that presentation. If there's any last minute questions in the online chat, please go ahead and post your questions. Otherwise, this will conclude this session. We do appreciate 2468. Team appreciate for joining us today. So last call for questions in the chat. We'll give it a minute or two for them to show up.
Oh, I was just going to ask about that. Thank you for putting that the link up, the ABM design calculator. If you could make sure put that link in chat. And then did you guys answer the other question that I saw Jason put in?
Yeah, they did, Mike.
Okay.
All right,
I'm
well,
sorry.
team, we do appreciate your time today. Thank you for being part of the inaugural FIRST Robotics Competition Texas workshop. And with that, we'll close out for now, and we'll see you back for the next session. Thank you. This concludes this session. If you're watching us live, please take the time to go back to YouTube and pick up our next session, or you can always visit our live page at firstrgv.me/live and pick up the next session there. We appreciate you watching and participating in today's session.